Today, we will learn about different architectures of Retrieval Augmented Generation to build more accurate, reliable, and useful AI applications. With RAG, we help companies and customers improve user satisfaction and save them time by ensuring correct AI output. As RAG has evolved, different architectures and approaches have emerged to address specific challenges and use cases. In this video, we will dive into these variations to help you choose the right approach for your needs. By the end of the video, you will know your options for RAG architecture and criteria for selecting the right one based on your specific requirements. Before diving into specific architectures, it's important to understand the difference between basic and advanced RAG implementations. Basic RAG follows the straightforward process. Convert documents to embeddings and store them, embed the user query, retrieve similar documents, augment the prompt with retrieved documents, and generate a response. This approach works well for many applications, but it has limitations. It treats all received documents equally. It doesn't adapt to different types of queries. It doesn't have mechanisms to verify or refine the retrieved information. And it performs the single retrieval step. Advanced RAG addresses those limitations through different enhancements. It has multi-step retrieval process, dynamic query reformulation, relevance filtering and re-ranking of the results, various self-correction mechanisms, and specialized architectures for different use cases. Now we will explore different RAG architectures. Cache Augmented Generation preloads relevant documents into a model's context and stores the inference state, key value cache. It maintains a cache of previous computations to avoid redundant processing. It is particularly useful for repeated queries or similar questions. Cache Augmented Generation reduces latency for common queries. Cache Augmented Generation is well suited for applications with predictable query patterns, for systems that need to optimize for response speed, in scenarios where users frequently ask similar questions. It's good for applications where computational efficiency is critical. Agentic Rag, which is also known as retrieval agents, introduces the decision-making abilities into the retrieval process. The system can decide what to retrieve, when to retrieve it, and how to use retrieved information. It uses an LLM to decompose complex queries into subqueries. It performs multiple retrieval steps based on intermediate results and can use different retrieval strategies for different types of information. Agentic Rag is good for complex queries that require multi-step reasoning, where different types of information need different retrieval approaches, and in scenarios where that initial query may be incomplete, and for use cases that require sophisticated information synthesis. Corrective Rag adds mechanisms to verify and refine retrieved information before using it to generate responses. It includes a verification step to check the relevance and accuracy of retrieved information. It filters out irrelevant or contradictory information, reformulates queries based on initial retrieval results, and also may use separate model to evaluate retrieved content. Corrective Rag is used for applications where accuracy is critical. So for domains with potentially contradictory information sources and where information quality can be different from use case to use case. Self-reflective RAG uses feedback loops where the model evaluates its own performance and adjusts its retrieval strategy accordingly. The model assesses the quality of its own responses. It identifies when retrieved information is insufficient. It may reformulate queries or adjust retrieval parameters based on its self-assessment. It learns from successful and unsuccessful retrievals. Self-reflective RAG is a good fit for applications for high precision when there is a lot of different user query types. It's good for systems that need to improve over time and where query intent may be ambiguous. RAG Fusion combines multiple retrieval methods to improve the quality and diversity of retrieved information. It uses different retrieval algorithms in parallel. It can combine dense retrieval, sparse retrieval, and hybrid approaches. It is good for using different embedding models for various types of content and aggregating and ranking results from multiple retrieval methods. RAG Fusion fits for applications with different content types and performs well where different retrieval methods have complementary strengths. It's a good fit for use cases when you need both precision and recall in systems dealing with complex, multifaceted queries. Temporal augmented retrieval specifically addresses time-sensitive information by incorporating temporal awareness into the retrieval process. This architecture considers document recency and temporal relevance. It may weigh more recent information higher for certain queries. Temporal augmented retrieval can handle queries with explicit or implicit temporal constraints and maintains awareness of information freshness. It's great for news applications or current events analysis, financial or market data applications. It is also a good fit for any domain where information changes rapidly, where the time context is critical. Plan then RAG introduces the planning phase before executing retrieval operations. The system first creates a plan for how to approach a complex query. It breaks down complex questions into simpler sub-questions. It determines what information needs to be retrieved and in what order, and synthesizes information from multiple retrieval steps. Plan RAG works for complex research questions requiring multiple retrieval steps and for applications dealing with multi-hop reasoning questions. It is key for use cases where query decomposition improves results. Graph RAG uses knowledge graphs to enhance the retrieval and reasoning process. In this architecture, the information is represented as a graph with entities and relationships. It can follow relationship paths to find relevant information and enables reasoning about connections between different pieces of information. This approach provides structured context versus just text chunks. Graph RAG is a solution for applications with complex relationship between entities and for use cases where relationship information is as important as entity information. FLAIR incorporates active retrieval augmented generation to improve response quality. The model generates texts and proactively identifies claims that need verification. It retrieves information specifically to verify those claims and can correct itself during the generation process. As a result, it reduces hallucinations by checking facts as they're generated. FLAIR works well for applications requiring high factual accuracy, especially where hallucinations need to be avoided. It's good for use cases generating long-form content with many factual claims and domains where verification is critical. Contextual retrieval improves relevance by adding context to document chunks before retrieval. This architecture enhances document chunks with additional information. It may include document metadata, section headers, or surrounding text. It improves semantic matching between queries and documents and saves important context that might be lost in simple chunking. Contextual retrieval works well for applications with structured and very complex documents. It's good for scenarios where document structure provides that important context and simple chunking loses too much of that. It's more common in domains with specialized terminology or concepts. Selecting the right RAG architecture depends on your specific requirements. For simple, factual queries, basic RAG may be sufficient. For complex, multi-step reasoning, consider Agentic Rag or Plan Rag. If factual accuracy is critical, consider Corrective Rag, Flare, or Selfreflective Rag. For diverse content types, RAG Fusion may be the best. For highly structured information, Graph Rag could be more appropriate. If recency or timing matters, then Temporal Augmented Retrieval should be considered. For high-throughput applications, Cache Augmented Generation may offer efficiency benefits. Many production RAG systems combine elements from multiple approaches to address specific requirements. This field is rapidly evolving, so new architectures and techniques are emerging all the time. Now that we've explored different RAG architectures, let's discuss the key implementation considerations that will help you build effective RAG systems. Chunking strategies is how you divide your documents into chunks. There is no one-size-fits-all approach, but there are some main strategies. Fixed size chunking. It divides text into consistent size segments, for example, 512 tokens each. It is simple to implement, but may break semantic units. It works well for content that looks the same, and fixed size chunking includes overlap between chunks to avoid breaking content, usually 50 to 100 tokens each. Semantic chunking divides text based on semantic boundaries, for example, paragraphs, sections, or topics. It saves the coherence of information. It requires you to understand the document structure. So semantic chunking is more complex to implement, but frequently yields better results. Hierarchical chunking creates chunks at multiple levels of granularity, for example, document, section, paragraph. It enables more flexible retrieval based on query specificity. It's especially useful for long or structured documents. Optimal chunk size depends on your specific use case. Smaller chunks, from 100 to 300 tokens, are better for precise factual retrieval. Medium chunks, from 300 to 500 tokens, have a good balance for most applications. Larger chunks, from 500 to 1,000 tokens, may be better for preserving context in complex topics. Experiment with different chunking strategies and evaluate their impact on your specific queries and content. Embedding models are really important in RAG architecture. Your choice for embedding model directly affects retrieval quality. So we need to consider a range of different factors. Model quality. Higher quality models generally produce better embeddings. Check the massive text embedding benchmark leaderboard for different comparisons, but popular options include OpenAI's text embedding, Cohere's embedding English, and open source models like BGE and E5. Model dimensionality is a key factor. Higher dimensions can capture more nuanced relationships. Lower dimensions are more computationally efficient. Another factor is domain specificity. General embedding models work well for broad topics. Domain-specific models really work well for specialized terminology. Consider fine-tuning embeddings for highly technical domains. Multilingual support is another consideration. If your content spans multiple languages, make sure your embedding model supports them, because some models are specifically designed for cross-lingual retrieval. Cost and latency is always a critical decision-making factor. Hosted API models like OpenAI or Cohere are easy to use but have ongoing costs. We should always consider throughput requirements for production systems. For knowledge bases, your vector database choice affects scalability, query speed, and maintenance complexity. They can be managed or self-hosted. Managed services like Pinecone or Azure AI Search, they reduce operational overhead. Self-hosted options offer more control and potentially lower costs. Scaling considerations help you understand how many vectors will you need to store. What query throughput do you require? Do you need real-time updates to your knowledge base or not? Some vector databases support advanced features like metadata filtering to narrow search based on non-vector attributes, hybrid search combining vector and keyword search, support for multiple vector indexes or collections, and replication and backup capabilities. As with any database, integration is really important. API compatibility with your technical stack, authentication and security features, monitoring and observability tools, these are the things that you need to ensure you have in mind. The way you structure prompts for RAG systems significantly impacts performance. Context placement is where in the prompt you place retrieved context. It really matters. Typically, it works best before the user query, but may need different structures for different LLMs. Instruction clarity is really important. We need to be explicit about how the model should use the retrieved information and specify if it should quote information directly or synthesize it in some way. We should also indicate whether to acknowledge information gaps. When we require source attribution, we need to instruct the model on how to cite sources. So we can consider including document metadata in the context and choose the balance between citation details and response conciseness. Implementing RAG is an iterative process, and it requires ongoing evaluation. There are a couple of key metrics we need to always keep in mind with RAG. Relevance is understanding if the retrieved documents are relevant to the query. Accuracy is about checking whether the generated responses are factually correct. Completeness is about checking if responses address all aspects of the query. And groundedness is about verifying whether responses are supported by the retrieved context. To verify efficiency, there are several options for evaluation metrics. Human evaluation is for subjective quality assessment. Automated metrics like ROGUE or BLEU, bilingual evaluation under study, or custom relevance scores. Side-by-side comparisons with baseline systems, and of course, tracking of user feedback and satisfaction. It is important to monitor and log retrieval and generation performance, identify patterns in failure cases, and regularly update our knowledge bases. We should also continue experimenting with how different components and configurations affect the end results. There are many frameworks that can accelerate RAG implementation. For example, LangChain or Llama Index provide comprehensive frameworks with built-in RAG components and specializations for data indexing and retrieval. Many frameworks provide pre-built components for document processing, embedding, retrieval, response generation, significantly reducing our implementation time. By carefully considering these implementation factors, we can build RAG systems that deliver accurate, relevant, and helpful responses across a wide range of applications. Now you're familiar with different RAG architectures, from basic implementation to advanced approaches like Agentic Rag, Flare, or Graph Rag. Each of them offers different capabilities suited to specific use cases. You also know the criteria that can help you choose the right architecture. You learned about different chunking strategies, options for embedding models, vector databases, and evaluation criteria for RAG efficiency. If you are a developer or an architect working on AI adoption with a variety of customers and use cases, this knowledge is critical for achieving the most accurate LLM results. Make sure to subscribe to my channel and like this video. Thanks for watching, and I'll see you in the next video.
Your reality has changed. You're stuck in your career. You're either using AI or being used. Do you still believe success is guaranteed? You feel it's time to wake up. Old strategies don't work anymore. Welcome to the real world. It will never be the same again. You need to fight for your future. Learn to spot truth from lies. I will help you. Together, we will win.